the afternoon session. We're very happy to have Christoph Kern here to present on some very cool applications of multi-calibration and this line of work to problems in survey statistics and conditional average.
Yeah, thank you very much. I'm very happy and excited to be here in person. So thanks for the organizers for putting together this awesome workshop. So this is joint work with Angela Chu and Michael, and we're interested in robustifying Kate estimation using multi-accurate learning. So motivation here is that basically causal effect estimation is important. So especially we're looking here at personalized causal effect estimation as a critical component to cut target decision support. And an example could come from the labor market context, which is where we have done some research. And you could just think about support programs that might be available to job seekers. And we might be not just interested in looking at the overall effectiveness of a given support program, but also we might be interested in heterogeneous treatment effects. Now, clearly there's a lot of work that is being done in this area. Specifically, we are here interested in looking at unknown deployment settings. So the question of whether we will be able to adapt personalized causal effect estimates to new settings. And specifically here again with this example, you might want to understand the program effectiveness in other contexts, and other contexts could just be other countries, right? So in Europe, there's this European network of public employment services that are supposed to learn from each other. So the idea here would be maybe one country runs a program, and we want to understand whether and how this program might work out in other countries. Good, and we will draw on previous work on our work on universal adaptability that is similarly kind of following this setup. So in that context, our task or inference challenge was that we are given one single source data, and we're interested in making inference on downstream target data that may not look like the source data. And we potentially also have many different targets. Sort of target specific approach to approach of this problem would be simply using inverse propensity score weighting, essentially, so that we would model the shifts between the single source and the given target at training time, so that essentially we would be able to adapt to this shifted downstream distribution. And we were interested in this paper in sort of moving towards a more target independent approach, as opposed to this very target specific approach where we would have to kind of essentially build a new propensity model for each target distribution. And to be a little bit more precise of what we wanted to achieve. So we're kind of talking here about a prediction approach. So we are kind of looking at a single predictor, and we're making some requirements as to how we would think about this predictor and how it would compare to target specific inference using propensity scoring. So what we say here essentially is that our goal of universal adaptability is that we have this single source distribution. We have a predictor that is learned on the source distribution, but then the estimation error that is based on this predictor, p tilde, is essentially competitive with target specific propensity scoring. So that is sort of our goal here, so that for each of those targets downstream, we are able to compete with this sort of best-in-class kind of propensity scoring approach using this single predictor p tilde. Now, how do we achieve this? It turns out quite nicely that multi-calibrated predictors are actually universally adaptable. So we can use a multi-calibrated predictor here as shown in this little sketch, and essentially pair it then downstream with different covariate distributions. And then if we would kind of compare this multi-calibrated predictor and the associated estimate on all of those different targets, we would have some guarantees that this is actually competitive to target specific inference using propensity scoring that is tied to each individual target downstream distribution. So in this work, we thereby kind of established this connection between those two rather different goals. So the fairness goal, where we're interested in protecting subpopulations from miscalibrated predictions, and kind of explored this connection to statistical inference, where we eventually want to ensure unbiased estimates on multiple downstream targets. Yeah, and however, in this work, our kind of estimates were kind of centered around this, what I would call descriptive inference. So for the most part, we were interested in some kind of mean estimates on our downstream population, or some estimate of some prevalence, which is now kind of immediately pushing to this follow-up question, which is, can we use this idea of universal adaptability to essentially robustify conditional average treatment effect estimation as well? So can we use multi-calibration and multi-accuracy to robustify and protect against shifts in the context of Kate estimation? So the case estimation setup is, of course, somewhat different to what we did in universal adaptability context. So we have our covariates. We now have some treatment indicator. We have observed outcomes, but however, we are, for the most part, of course, interested in the potential outcomes. So YT. And our estimate of interest is this Kate function. We were essentially kind of looking at the difference in the potential outcomes given X, so that this is sort of personalized in the sense that given your X set in X, you would get potentially a different estimate for your treatment effect. Right, then of course we are drawing on assumptions that are kind of standard assumptions in the causal inference context. Of course, most importantly, this unconfoundedness assumption, which is just saying that, okay, in our covariates, we do observe all of the potential confounders that we might worry about. Although actually later on, we, to some extent, relax this assumption and see what we could do in a, let's say, a slightly different context. Good. So then what do people do in this context in order to learn this Kate? There are, of course, a bunch of approaches that have been proposed. For the most part here, we will focusing on the T-learner, which is rather, let's say, a prediction approach to solve this problem. So we have two steps. We first have this idea of simply fitting treatment conditional outcome regressions. So for our treated and untreated in the data that we observe, we're fitting, for instance, a random forest or something else. So we have those two arms that we are establishing in order to learn the respective outcome functions. And then we are imputing the respective counterfactual outcome using those two arms in order to estimate and the Kate function. So that is sort of a common approach. Clearly, there are also more sophisticated approaches that have been proposed in this literature that are, for us at this point, maybe reference methods, but we're also moving towards understanding whether we could also do something about pairing multi-accuracy with those approaches. But for now, we'll just focus on this simple T-learner setting. Right, performance estimation. Here we would, for instance, be interested in looking at the MSE of the Kate or bias, although again, our main thinking here is that we are interested in understanding how this might work under distributions that are different than the distribution that we would use during training time. So it's again the same idea as before. What would happen if we have like this unknown shift during our deployment in the deployment setting? How do we perform then under shift? And let me also again sketch this higher level idea. So this is the first setting, the external shift setting. We have given this first set of unconfounded data, so with x, t, y. We are then trying to estimate this Kate function. And our idea for the most part here is simply using MCBoost auditing then in order to robustify this initial Kate learner such that during deployment time, we are protecting against distribution shift eventually. We directly jump into what we propose to do. So this is our higher level algorithm, or kind of summarizing this rather simple idea, which is just saying, as I just mentioned, so the input is our observational data that is unconfounded. We have some auditor function class F. We have our function class that we would use for outcome function, modeling the outcome functions. Again, in practice, it could just be some random forest. And then the first step here is essentially following this t-learning idea. So we fit our two outcome regressions for treated and untreated. And then we simply propose to post-process both arms of the t-learner, so the model for the treated and the untreated, using MCBoost auditing. For the most part here, we'll just draw on multi-accuracy. So we'll do multi-accuracy auditing such that this condition here holds, so that for every subpopulation in F, we are multi-accurate on both arms now. So this is like, again, for those two outcome functions, we are multi-accurate eventually. And we are then essentially using those post-processed outcome functions to return our multi-accurate Kate estimator T tau tilde. A slightly different setting where we are essentially proposing a similar idea, but this is now complicating things a little bit. So here now we say, okay, what if our observational data is not unconfounded, such that there is some unobserved confounding, so this U variable here that is not observed, meaning that by just using this observational study, there's no hope to actually learn the true outcome, the true Kate function, right? So we're kind of in the unobserved confounding setting. However, we also assume now here that maybe we have access in addition to a small randomized controlled trial. So in this case, then we might be able to essentially jointly learn from those two data sets. So again, here the assumption would be maybe this RCT data is so small that it's also not possible to efficiently learn the Kate from just this small RCT data. So we want to kind of leverage sort of both data sets. And we would do this again by using MC boosting. Essentially, the key idea here was simply to say, okay, we'll warm start a t-learner on this observational data, and then we post-process on the RCT data. So that was like the idea of connecting those two pieces. With then eventually the hope that we will get rid of the bias that comes in from the confounding in the observational data, and at the same time, possibly correct or be robust towards unknown downstream covariate shifts. So for this, also again, like just highlighting this simple idea. So now we have this confounded observational data as input in addition to this small RCT. Again, some auditor function class and function class for the outcome functions. We start now with building a t-learner in the observational data set. So we again have our two arms of the t-learner, and then the RCT data comes in when it comes to post-processing this initial t-learner for multi-accuracy, again, with respect to those both arms, the two arms of the t-learner. And then eventually we are again returning this multi-calibrated tau function.
Interpret the boosting test function as like evidence of specific kind of confounding or something, because you're saying this is the way that the conditional expectation is most different from the confounded distribution of the randomized experiment.
In terms of like after the fact,
well, when you actually do your AC boost, you will get a test function, which is like the boosting layer. That's the place where the RCT and the confounded data is the most different in terms of the conditional expectation. You interpret that as like evidence of a particular type of confounding structure.
Interesting. I think we would not like consider that at this point. Yeah, cool. Even checking like how much like checking or recording the number of iterations that is needed at all. Yeah. So yeah. Okay. Yeah. Yeah. So in terms of like the technical results, so I'm just summarizing a little bit what we can say at this point. So some main characteristics of this multi-accurate post-processed KT learner. So first we can establish a do no harm property with respect to the MSE, saying that essentially comparing to the best in class T learner, we are at least compatible or competitive with respect to MSE to that best in class T learner. And also then in addition, of course, we want to see some bias guarantees with respect to those unknown shifts. And in order to establish those, we essentially assume that we are able to capture sort of a rich class in our auditing function that include two pieces. So C here, which is including or indexing the subgroups that are relevant for the Kate estimation, and also H, which is relevant to capture the downstream shift. So if we're able to essentially assume that our auditing functions include the product class of those, then we are able to establish this bias guarantee that is saying, okay, on all of those downstream distributions, we are sort of in a safe space with respect to bias. Right, so we have run quite a few simulations to see not only whether this initial idea works out, but also compare to other approaches that are common. And the setup is we are starting with simulating, of course, our x, t, and y's. We also then know the true Kate function that we can compare against. And then we are also sampling from this initial distribution with weights to introduce a shift in the covariate distribution. And we do this by following this external shift function that is including also different shift intensities, so that we can compare against like over a range of shift how strongly this guarantee actually holds. And then again, those two settings to be a little bit more precise with what we did here. So setting one, external shift and observational data only, non-observed confounding. We are training on this initial OS distribution. We have an additional small auditing sample from the same distribution. Again, we are kind of, that's important, so we don't want to cheat here. So we are kind of auditing on the same source distribution, and then the deployment distribution, also the test data here is shifted, so that is where we then evaluate MSE and bias and all of the things. But for setting two, observational data and small shifted RCT, we have this additional unobserved confounding in the observational data. And here now the training happens on this first DOS distribution. We are then proposing, as I mentioned earlier, to audit on the RCT. Here the RCT is also shifted in the covariate distribution away from the OS. And then we are again back and evaluating MSE and bias on test data that comes from the original distribution. Although we could also have like an additional shift for this deployment data, but for now this is just a sort of predicting back the observational distribution. I am comparing to for now two reference approaches. So we are comparing against causal forest in both settings. Causal forest trained on the observational training data alone. Then, of course, we are comparing against the unprocessed T-learners. So our kind of initial T-learner, in this case, using random forest, trained in the observational training data. And then we are interested, of course, in evaluating how our combined approach works. So we have our T-learner MC-rich, which is using this initial T-learner post-processed with MC-boost using, in this case, rich regression in this auditing set. And here for setting two, again, causal forest, t-learner, and t-learner MC3, where now the post-processing happens with decision trees in the RCT data. But also, this is just for just picking things here. We also did the tree post-processing and bridge post-processing in setting 2 and 1 as well. And also there are more things that we compared against. For instance, we also compared against sort of reweighted causal forest and reweighted t-learner, where we are kind of first estimating a propensity score in order to then correct for the shift and essentially reweight the source data so that it looks like the target data, and again train the t-learner on top of that. Although of course that needs access to the downstream data at training time. So this is sort of a strong baseline that we could compare. Then what do we see? So this is the MSE over multiple simulation runs. In the no shift setting, we don't expect to see anything surprising. So clearly it's just showing that MC rich here on top of t-learner doesn't hurt, at least. And then the main finding is that moving to this moderate shift or strong shift setting, especially if we are training with sort of a modest size of initial observational data, post-processing this initial t-learner with MC rich improves MSE in the downstream distribution to some extent. Whether this is a significant improvement is maybe up to you to decide. But we do see some improvements, especially in those settings where we have limited initial data, and there's also maybe some improvement also later on. But for the most part, we see the biggest boost there. For setting 2, so again, this is jointly learning in the observational data and the RCT. There's a little bit of an additional performance gap that we see. So also here in the no shift setting, reminder here that the shifted data is here now the RCT, so the RCT is shifted away. So meaning that also we would here now actually see something interesting in the no shift setting, because here again the RCT data is the data that is allowing us to learn unconfounded gates, meaning that here actually there's a let's say it's a significant improvement if we compare the original blue t-learner to our post-processed t-learner, which is the green bars. And this is also consistent then if we move the RCT data away from the observational data in X. Although we also do see that it's hard to here to off-the-shelf compete against causal forest at this point. Good. Yeah, and I'm already concluding here. So our idea was to see whether we can robustify KT learning to unknown shifts using MC-Boost post-processing. Also, this other setting was kind of trying to learn jointly from observational data and RCT by utilizing MC boosting. We do see some improvements in bias and MSE in our simulations at this point. We also did a real data application that is sort of in line with what we've seen in the simulations, although it's also important to note at this point that it's our multi-K approach is sort of robust, but it's not as efficient, such that, for instance, it's hard to compete against learners that are kind of optimized for reducing bias, such as causal forest, for instance. Right, but also wanted to stress here that clearly this is an area where kind of a lot of work has been proposed. Our focus here was for the most part to just push this idea and then see whether we can use multi-accuracy and multi-calibration in an off-the-shelf manner and adapt it to this Kate estimation domain. So again, this is sort of an ongoing research, and we hope to move this further. And yeah, so that was sort of the main takeaways. I also wanted to just at the end stress that since we all learned that all that we need is multi-calibration, we develop an R package. So also wanted to just make sure that this is out there and people know that this exists. We are also clearly happy to receive any feedback on this. Yeah, I think it has a rather straightforward interface. So what you can do, you can essentially use plug in your favorite ML model. We have some predefined auditing algorithms, but you can also use something else there. And then you basically just need 2 or 3 lines of code to multi-calibrate your model and then use it downstream for whatever you like. Right? Yeah, that's it from me. Thank you very much.
For the package, are there a lot of like hyperparameters? Like, do you have to specify a number of
You can. So it's yeah, that's all like something that can be specified. So you can also say, okay, I want to hard constraint on the number of iterations. That is all. Yeah, and also sort of think about this as a tuning problem, maybe. So that is included. You also include like things like cross validation on the auditing set, so that you're not sort of overfitting if you're in the calibration context, but yeah, so that is all possible to adjust.
And so for the actual experiment, did you have to optimize for this a lot, or it kind of like worked out at the box?
Oh yeah, actually we sort of were rather, let's say, agnostic here and sort of mostly used like the MCU setting of like the standard setting that we just opted for in the package. Setting. So yeah, that was not like too much like optimization that we did on that.
Any last questions before we finish this?
So how sensitive were these results to the choice of auditing algorithm?
Yeah, so as I mentioned, so we did use trees and rich regression in those settings. I would just from the top of my head now say it was pretty similar. I think I am sort of reporting rich regression here and tree regression just to not have everything on one slide.
But the settings are different, right? So but it was similar in both settings for both methods.
Oh, yeah, sort of, yeah. And also what I do remember is that we, like there's like just a limited number of rounds that actually was needed here. So it's not that this is like not running MCUs for like 50 rounds or something. It was just like minor post-processing, and we always see like those differences.
Okay, great. Let's thank Christoph.